Hello and servus. Today I will show you on using the state monitor from the CATS library. If you are more new to the CATS library in general, you might, or to purely functional programming in general, then you probably read about the state monitor and ask yourself, how would I use it in order to program anything useful? At least for myself, it was a big question mark in the beginning. You've probably read about Scala and CATS in one of the underscore.io books. It's called CATS with Scala. There you will find an application of the state monad for when they use it to write an interpreter or a parser as a final exercise. So if you did this exercise, I think this tutorial might be a good next step for you to proceed. So as you can see, I'm using the new Metals plugin, and here in the terminal I'm running Bloop. So whenever I change something in the code, it immediately compiles and gives me the output. So I want to program in Scala in a purely functional way, as you can see, because I'm extending the IO app, and I'm returning from my main function an IO with an exit code. Here in the build SBT you can see I'm relying on two compiler plugins. I'm not sure if I really need them here. As dependencies I have the CATS library as well as CATS effect. So let's get started with this simple task. So step 1, as input we get a list of Roman characters, something like a list of X and M and I and D and M, and you find the definition of these data types here. You can see this Roman symbol M extends a Roman. It has this symbol and the value is 1000. Here the Roman symbol L has the value of 50. So the first step, we just get a list of them. As in the second step, we have the task that we need to inspect this list pairwise. So you can see in one step we should inspect the X and the M, then the I and the D, and the M and and probably nothing. So if the first character is greater than or equal to the second, we create an addition expression, otherwise we create a subtraction expression. Greater than this, so comparing Roman characters relies on this value here. And as output we want simply a list of expressions, so something like a list with expression plus, expression minus, and expression literal. So before we proceed, we need to have the input for the state. So then I will simply define a case class wrapper around this list of options. And then as the next step, I will define a type alias for state. I call it rState together with a type parameter a. So at this point, just as a refresher, what is a state monad? State monad is nothing more than a wrapper around a function. As input to the function you give it an R input, and as output it gives a tuple of a new input R input together with a created value. So the function actually has the signature of this R input, and what you get back is a new transformed R input. How you want to transform it, it's simply up to you and to what you want to program. You get back a new R input together with some created value, whatever this value is. So when we look at step 2, it says we need to inspect the list pairwise. Yeah, so we will just write a simple function which extracts the first item from the list, and as new R input it will just set the tail of the old list. So here def pop, here I immediately want to pattern match on the input. So the input is of course of type R input, and here also pattern match on the list in order to destructure the head from the tail. And what we want to have back is a new R input. That's our new state with XS, and the created value is simply the head of the old R input. So then when we want to inspect the list pairwise, that means something like this and this, and the M, there exists only the first item. So the second item we need something to see if a value exists or not. So it will be a similar function like pop, but just the function we will write serves just as a look ahead on the next element, and to see if it exists or not. It does not change the list. It simply gives you an option of an element to inform you about that it exists or not. So def peek. So here's the option from a Roman. In, of course, is our R input, and our new state is again in, because as I said, we do not want to transform the list in the peek function. We only want to look if we still have elements in our list. So it's something like in characters and the head option. So by having we created these two small functions, we could program them without looking at more at a larger context. We could really have our focus only on implementing this function or this function. And the power of functional programming comes of course from composition. Yeah, and so we will use these two functions in order to define our pairwise function. So def pairwise gives us back a new R state. With an, as you can see here, with an expression plus, expression minus. So these are types I will simply copy over, because they are not very interesting in the context of the state monad. Here we just define a sealed trait and two data constructors. One is expression literal, expression for it's simply meant to be meant as a node within an abstract syntax tree for plus operations, and here is expression bin minus. So we continue with our pairwise function. So here we will get the first element from the list, call it A, and we get it from pop. And B, we will peek. Yeah, here as you can see, if you call peek, you get a state within, you get a state which contains an option which contains the value you're interested in. So if you have something like this, that you have nested structures of monads, you should immediately think of using a monad transformer. This is exactly what we will do now. Yeah, and how do you find out what monad transformer you should use? So it helps at least me when I use the inner monad. It's called option, so we will definitely have to use the option transformer. And the option transformer is a wrapper around our R state and our option. And option T behaves like an option. Okay, so it's a wrapper around R state and an option, and it also behaves like an option. So if you call map or flat map on this option T, on this option transformer, it actually flat maps or maps into the state and into the option. Yes, so you can save a lot of typing using these monad transformers. So here in this case we use the option transformer, option T. Then here we call peek. So that means we want to flat map here. So that means if this is successful, then it will flat map, and you will see that it is this parse Roman, which is contained in the state and in the option. And here you can decide what you want to do. So here, when we peeked, it means there exists a value, and as long as a value exists, we also want to pop it. So here we peek. If the value exists, then of course we also want to pop it, and by popping it means we also want to transform the remaining list here by deconstructing. So here it's again option T, and here we want to pop, and then we need to map the value into an option, because this is what option T expects. So as you can see here, when we pop, we're in the context of a state, and here we're in the context of option T, so that's not compatible. So when you want to have the underlying value again, we need to call here value. Yeah, as you can see here, we defined the value from the peek, but it's actually not interesting. We do not use it here. So there's a symbolic operator which is exactly for this situation. It's this, and here we can save one parenthesis. So that That means here, as long as the peak is successful, we also pop the value. Yeah, so then we will need to construct our expression value. One second. Okay, there's something missing. Yeah, of course we need to have parentheses around this expression. And here you can see that it has the correct. So I will just make a small trick in order to see if everything was correct. Yield expression. Oh no, A. Yeah, you see the A is a Roman and the B is an option with Roman, so it all was correct. Yeah, and the terminal, it's from before. You can see that the bloop also says that everything looks good. So here we need B is an option which we can fold together. So for the case it is empty, that means that this was successful, that was successful, A is successful and the B is not successful. So in this case we simply want to put an A value in an expression. And we use our expression literal for this with an A. And in the other case, for the case that A is bigger than or equal to B, it was in our requirement here that the first character is greater than or equal to the second. In this case we should add them together, so we create an expression node for plus, expression plus with an A and a B, else expression minus with an A and a B. So we'll see if that was correct. Second. Yeah, this was missing, and yeah, of course we need to here we could of course compare the values here, but we want to simply write an ordering using the cat's order type class. So object a Roman implicit order compared to B. So comparing our Roman values is based on the values, of course, and here it's some B value missing. So here you will see that our comparison works. Not found expression. Yeah, it's not correct, of course. Like this. So, and here we will simply use our expression. So cool. What did we do? We have our function pairwise, which we composed of other functions of pop and peek, and here we converted where we combined state with an a Roman together with a state of option of a Roman into a state of an expression. So that means we can evaluate our input pairwise. Yeah, but pairwise is not enough. We need to combine. So now we will add another layer. Our base layer was implementing pop and peek. Based on them, we added pairwise, and based on pairwise, we now implement our next layer for evaluating all of our input list. So we will call it combined states. List with expressions with a Roman, and whenever we compose monods, we use for comprehension. So that means here we have our pairwise expression, and then we need to look at the current state. So it means state get, and then we construct our expression list. So this will be a recursive function. Expression list, and here we will see that if our state one second here. Yeah, here by adding the expression after yield, the code completion works again. So just if the size, as long as it is bigger than 1, we will combine the states, and if not, so that means we only have one element in our list. That means we can pop and map into a list of expressions. So, and the last step would be to combine the list again with the expression list. So if everything compiles, I'm very happy. Yay, it does. So then we simply need to, we can try it out. So here we will our input list. Our result is, it means we combine states. We run our function with the R input as we defined. Then let's say we will rsym m and rsym d, rsym c, rsym l, rsym c, and this last rsym m. So here in our IO we simply print the value. No. Result value. What is it? What is it saying? 5 minus. Yeah, we'll simply copy it over. It's here we'll see that our result list consists of expression binary plus, then expression binary plus again, then expression bin minus. You can see that it is correct because it's L and C, and the L is smaller than the C, and as last it's our rsym m, and after that it's over. So yeah, I would be happy if you have any comments or questions. Then yeah, just ask them on discuss on my blog. I would prefer this location and not having any tag conversation on YouTube. Yeah, so if it was helpful, I'm very happy, and yeah, we will see us hopefully on the next video tutorial. Bye bye.